Today we're going to wrap up our survey of conic sections by discussing our fourth and final type, namely the parabola. Now parabolas are interesting because we've thought about those before this year in the context of quadratic equations, right, as the graph of a quadratic equation, but in the context of conic sections we can give them a different definition. Okay? So for a conic section point of view, a parabola is the set of points x, y in a plane equidistant from a fixed line called the directrix and a fixed point called the focus that is not on that line, the directrix. So jumping down here to this diagram, you can see we have our focus there, we have our directrix, this line, and the red parabola that we have produced is made up of points that are equidistant from these two objects, the focus and the directrix. So you can see this point P1, okay, that lies on the parabola because its distance from the focus, the length of that line segment, is the same as the length of the line segment connecting to the directrix down here. So P1 D1 equals P1F. Similarly, we have another point over here, P2. The distance to the focus, P2F, is the same as the distance to the directrix, P2 D2. So every point on the parabola will satisfy that equidistance relationship. So casting our minds back, we hopefully recall that a parabola has that axis of symmetry that will always be perpendicular to that directrix line and also pass through the vertex. Well, what is the vertex of a parabola? Before we took it to be that turning point, but here, in the context of conic sections, we can take the vertex to be the midpoint of the perpendicular segment connecting the focus and the directrix. Okay. So previously we had two forms that we could use to represent a parabola. We could write the equation in vertex form or in standard form. Well, it turns out we have a new way of representing it, which we'll discuss shortly. So just like for our other conic sections, there's going to be a parameter, a constant, that tells us something about a distance in the diagram. So the absolute value of P is going to be the distance from the vertex to the focus and the directrix. Remember, the vertex is a point on the parabola, so those distances should be the same by definition of the parabola. So if we zoom in real close here, here is our vertex, here is our focus, so the length of that line is the absolute value of P, but also the length of the segment joining the vertex to the directrix will also be absolute value P. Let's remember, in standard form, that coefficient A of the x squared term controls whether or not the parabola opens upwards, like this, if A is positive, or downwards, like this, if A is negative. As a quick reminder, for our two different forms that we've seen previously, the axis of symmetry is given to us simply as x equals h if the parabola is described using vertex form, or if the parabola is described in standard form, we can do a little bit more work. The axis of symmetry is x equals negative b over 2a if we're looking at the standard form of the parabola. Where is the vertex? Well, vertex form is well named, right? Because for the vertex of the parabola given in vertex form, we just get to read off h, k. It's staring us in the face. Here's our h. Here's our k. Again, if we're in standard form, we need to do a little bit more work. Okay? If we're in standard form, the x-coordinate of the vertex will be that negative b over 2a quantity. To find the y-coordinate, we just have to substitute that x-coordinate into the rule for the parabola, and that will tell us the y-coordinate. So as we just discussed, we can define a parabola not just as the graph of a quadratic equation, but as a conic section. Okay, so the definition we saw involved that point. Remember, we called it the focus, and a line, which the focus point was not on, called the directrix. Now in doing so, we're able to actually come up with parabolas that open to the left and to the right. So something like opening to the left and opening to the right. Now these graphs very much fail the vertical line test. So they cannot come to us as graphs of functions, but with our conic section definition of parabola, they deserve just as much credit to be called parabolas as our opening upwards or downwards parabolas do. So here we have a table that's going to tell us everything we need to know about a parabola whose vertex is the origin. Think of this like our hyperbolas or our ellipses that were centered at the origin. We don't talk about the parabola as being centered, but we do talk about it as having a vertex at the origin. So if we want a vertical parabola, so one opening upwards or downwards, the axis of symmetry will be at x equals 0, and the equation will be x squared equals 4py. Now p is related to that distance that we talked about earlier, the distance from the vertex to the focus, or the vertex to the directrix. There's a 4 there just to make some of our quantities later on nicer to state. Don't worry about it too much, but certainly don't forget about it. Now if we compare this equation to our standard form for a vertical parabola, we can figure out that the parabola will open upwards if p is positive, and it will open downwards if p is negative. Okay. Now it turns out our focus for a vertical parabola will be at 0, p, and the directrix will be the line y equals negative p. So for a vertical parabola, we should expect that directrix to be a horizontal line, so we get y equals negative p. Similarly, we're expecting the focus to be on our axis of symmetry, so we're expecting that to be on the y-axis. Same deal if we're looking for a horizontal parabola. So this means we're going to open to the left. That's not standing out very much. Let's use this pen. Horizontal parabola opening to the left or to the right. Here, x and y interchange their roles in the equation. So we have y squared equals 4px. Okay. Now, p again controls the direction that the parabola opens in. So if p is positive, the parabola will open to the right. Okay, the way to think of that is positive p opens in the positive x direction. If p is negative, the parabola opens to the left, i.e. in the negative x direction. The focus is again given to us by p, but this time it's going to be on the x-axis at the point p, 0, and our directrix, which we're expecting to be a vertical line, will be at the line x equals negative p. So p is telling us a lot about our parabola. Let's see how we can extract some geometric information from the graph of a parabola to write down its equation. So here we have a picture. So what can we extract? Well, we see we have an axis of symmetry at x equals 0. We have a directrix at y equals 5. and our focus is 0, -5, and you can see our vertex is passing through the origin. So first things first, we need to extract some qualitative information from this graph to make sure we start off with the right flavor of equation. So first things first, because the axis of symmetry is vertical, okay, and we can see the parabola opens downwards, okay, we have a vertical parabola, so we're expecting our equation to look like this guy up here, x squared equals 4py. But because we're opening downwards, we're expecting p to be negative. So that's our baseline here. We now need to figure out what p is. Well, remember, in absolute value, p is the distance from the vertex out to the directrix, which should also be the same, right, as the distance from the vertex out to the focus. I can see both of those distances are 5 from the diagram. Okay. So if we call P the vertex and the directrix point on the y-axis D, 5 is the distance from the vertex to the directrix, which is also the distance from the vertex to the focus. So that's p in absolute value, but we'd already decided p was supposed to be negative, so that means p will have to be actually -5, just from the information given to us in the graph. So to finish off this problem, all we have to do is write down, substitute in p equals -5 into our equation x squared equals 4py, so our final equation is x squared equals 4 -5y, i.e. x squared equals -20y. Example 2 is similar, but they haven't given us the full graph this time. They've just told us where the vertex is and where the directrix is. So the vertex is at the origin, and the directrix is the line x equals -6. So let's throw that on there. Now, we know the distance from the directrix to the vertex will always be the same as the distance from the vertex to the focus. This distance here is 6. So to get to the focus, I need to go 6 in the other direction. That will get me here to my focus. So we need to remember, for a parabola, the parabola always opens up and gives a big hug around the focus. It focuses, you could say, on the focus, and it turns its back on the directrix. So what we're expecting to see here is a parabola focusing on the focus, turning its back on the directrix. So we can see here we're going to have a horizontal parabola opening to the right. Not sure exactly what it looks like right now, but something like that. So let's start running these steps here. So because the directrix is vertical, okay, the equation that we are looking for this time is y squared equals 4px. Now because we were opening to the right, we're expecting p to be positive. Remember, when you open to the right, p is positive because we opened to the right. So we need to find the value of p. We already decided from the given information the distance from the vertex to the directrix was 6. So in absolute value, p is 6. But p was positive. So that means p genuinely was 6. So to write down our equation, we'll substitute in p equals 6. That gives us y squared equals 24 px. All that's left to do is to sketch the graph. Now we want to have some idea of how steeply or narrowly the parabola is opening up. The best way to do that is to take a test point. So we may as well, for simplicity, take x to be 1. That gives y squared equals 24. So that means that y will be plus or minus the square root of 24, which is a little less than 5 in absolute value. So when I have x equals 1, I can take the positive root, a little less than 5. I can take the negative root, a little less than 5 in absolute value. And now I can just complete the arms of the parabola, making sure I hit those points. Let's add on the axis of symmetry for good measure at y equals 0. Example 3 here is going to unfold in a similar way. We've been told the vertex is at the origin, and we've been told the directrix is the vertical line x equals 1.25. So that's 1 1/4. There is our directrix at x equals 1.25. I can figure out where my focus is immediately, right? I need to go 1.25 in the other direction. That gives us our focus. So now we can get an idea of the shape of the parabola. I'm going to wrap around the focus, turn my back on the directrix. So I'm a horizontal parabola opening to the left. So that means that our p value will be negative. Okay. So let's forget about my little sketch. That was just for us, just for me. We're going to do a better sketch at the end of this problem. But because the directrix is vertical, we're going to get horizontal parabola. So the equation we need is y squared equals 4px, with p being less than 0, because the parabola is opening to the left. Need to find the value of p. Well, remember, p is this distance from the vertex to either the directrix or the focus. So in absolute value, p is 1.25, but p was supposed to be negative. So we need to take p to be negative 1.25. Our equation is therefore going to be y squared equals 4px. So substituting in, I will get that y squared equals negative 5x. I'm just cramming this on here so I don't have to change the page. And now to get an idea of the shape of the parabola, let's do one more point. Now we can be clever here to make the math work out nicely. Okay, let's see what I mean by that. If we take x to be negative 5 and we substitute in, we get y squared equals negative 5 times negative 5, which is just 25. So I get, taking the square root, y equals plus or minus 5. So by picking x cleverly, we managed to end up with a nice whole number y coordinate when we take that square root. So I end up with this point and this point on my parabola, and I can complete my sketch like so. Now sometimes the numbers are too big to choose our x cleverly like that, but it's always worth thinking. Is there a way I can make my y-coordinate nice when I take that square root? And just to wrap up the problem, we already wrote down the equation on the previous page. Let's do one more like this before we move on. So in this fourth example, we're told the vertex is 0, 0, and the focus is 0, negative 7. So that means the focus is right there. Okay, well remember our parabola passes through the vertex and opens in the direction of the focus. So that means we're expecting to see something like this. Okay, so our axis of symmetry is going to be the y-axis. So we'll erase this little sketch for now, because we'll do a better one later, but that just gave us enough information to get started. So because the axis of symmetry is vertical, the parabola will be vertical, and so the equation will be x squared equals 4 py. Because the parabola opened downward, we're expecting p to be negative. Let's find the value of p. Well, that is, at least in absolute value, the distance from the vertex out to the focus, which is 7. But remember, p was supposed to be negative, so we'll take p to be negative 7. Well, what else can we add on here before we press on? Well, if the focus was 7 units away, the directrix will be 7 units away in the opposite direction. So we'll have the directrix at y equals 7. All we have to do now is substitute this value of p into our equation to get that x squared equals negative 28y. So before we can do a convincing sketch, let's take another point on the parabola. Let's say take x to be 5. That gives us that y equals negative 25 over 28, just solving. So we can plot when x is 5, y is almost negative 1, so we'll have a point there. And because of the axis of symmetry, we'll also have that point over on the other side of the y-axis too. And so now I can complete my drawing knowing that I have a fairly shallow looking parabola. Let's now think about what happens if we have our vertex not necessarily at the origin. It looks very similar. The situation is the same, we've just carried out a transformation. So everywhere that we saw a y before, we will now have a y minus k, where k is the y-coordinate of the vertex. And everywhere we saw an x before, we'll have an x minus h, where h is the x-coordinate of the vertex. Okay. The axis of symmetry has also shifted. Okay, it's not y equals 0, x equals 0 anymore, it's y equals k, x equals k. And notice we still have that 4p in play in our equations. The direction of the opening of the parabola still totally determined by p. And the focus and the directrix also get translated around just like the axis of symmetry does. The best way to roll this out, I think, is with an example. So let's see how this is going to go. So we're asked to find vertex, value of p, axis of symmetry, focus, directrix of the parabola, and graph it, where this is our equation. X minus 2 all squared equals 8 times y plus 3. Now we've left that right hand side factored so that it's easier to read off by comparing to the standard form what the y-coordinate of the vertex is. So the vertex has x-coordinate 2 and y-coordinate negative 3. we need to find the value of p. Well, this time we're not reading it off from the graph, we're reading it off from the equation. Okay, so we have 4p comparing should be equal to that 8. Okay, if we look up here to our equation, that coefficient multiplying the y bracket is always 4p. So we get 4p equals 8, and therefore p is equal to 2. Now, since p is positive, okay, we already know what direction where the parabola will open in. Because we're looking at, a vertical parabola, okay, we can compare and see we have the equation of a vertical parabola. Because p is positive, our parabola will open upwards. So bit by bit, as we go step by step, we're learning more and more about what our parabola is looking like. Well, here, let's start throwing down what we have. So the vertex is at 2, -3, 2, -3. There is our vertex. We know the parabola is going to open upwards. Something like this. So let's draw that little sketch for ourselves. I know what P is, so I know where the directrix and the focus should be. So I should go 2 up to get to the focus and 2 down to get to the directrix. So we have the directrix at y equals -5, and the focus will be here at 2, -1. So I'm going to erase my little helpful sketch for now because I want to draw a more accurate one later. Last thing I can throw down for now is the axis of symmetry, which will pass through the vertex and the focus. So we have an axis of symmetry at x equals 2. Axis of symmetry x equals 2. The focus was at 2, -1, and the directrix was the horizontal line y equals -5. The last thing we'll want to do is get an extra point on the parabola so we can draw an accurate picture. So let's take, for simplicity, x to be 0. Substituting in, I get -2 squared equals 8y plus 3. So I get 4 equals 8y plus 24. And so y equals, if we solve, -5/2. Let's plot the corresponding point. So x is 0, I get -2.5. That's roughly there. By the axis of symmetry, we know I get a point on the other side of the vertex, 2. And so I can now draw my parabola fairly accurately, as so. Let's see another example together. We've summarized in a little table here the situation, the standard form, for horizontal or a vertical parabola, just to refer back to. So for this equation, notice, because the square is on the y term, we'll have a horizontal parabola. And because that 12 is positive, we know that P is going to be positive. And so we're going to open horizontally to the right. Okay, the vertex we can read off straight away as 1, 3. So let's throw that on there for my vertex. We can algebraically solve for p because that 12 coefficient is always going to be our 4p. So p will simply be 3. Now, because we know our parabola is opening to the right, I can throw down the focus 3 units to the right, and I can throw down the directrix 3 units to the left of the vertex. So that would be here. And that's at x equals -2. And we know we have our axis of symmetry passing through the vertex and the focus at y equals 3. So let's record this in our table. The focus, we can read off the coordinates as 4, 3, and the directrix occurs at x equals -2. Again, we should pick another x value to get another point on the parabola. Let's be fancy this time and actually find the x-intercept. We know because we're opening to the right that there will be one. So how do we do that? Let's set y to be 0 and substitute in. So we'll get -3 squared equals 12, x minus 1. If I solve for x, I should get x minus 1 equals 3/4, just dividing through by the 12 there, and so x is going to be 7/4. So that means our x-intercept occurs at 7/4, 0. So that is a little less than 2. So we should have that point there on the parabola. The axis of symmetry gives me another point for free, right there. Now we have enough information to draw a fairly convincing sketch of our parabola. Now this next example is trying to trick you because the equation has not been given to you in standard form. Okay? In standard form, the bracket that is squared is on a side of the equation by itself. So actually we need to rearrange here algebraically by multiplying by -2 on both sides. So that should give us x minus 8 all squared is equal to -2 y minus 4. If we had started doing our analysis to the original equation, we would have ended up with total nonsense. So something to watch out for. Now though we're up and running, we can read off the vertex lies at 8, 4. There's our vertex. For the value of p, okay, well, it's always that coefficient that will give us p. So 4p is equal to -2. So p is going to be -1/2. So let's think here. Is our parabola horizontal or vertical? Well, the fact that the square is attached to the x term means that we are a vertical parabola, and because p is negative, that means the parabola opens downwards. So to find our focus and our vertex, we should move half a unit above and below the vertex. So because we want to open downwards, the focus will be half a unit below vertically the vertex, and the directrix will be half a unit vertically above the vertex. So that is a directrix at y equals 9/2. Our axis of symmetry, as always, passes through the vertex and the focus. So we have our axis of symmetry at x equals 8. Our focus has coordinates 8, 3.5, right? I subtracted 1/2 from the y coordinate of 4 to move downwards, and the directrix, we added that half to the y coordinate of 4 to get y equals 4.5. To sketch our parabola, we need to find another point on there, another test point. And what can help us there is thinking about the domain and the range for this graph. Okay, so because we are opening vertically downwards, okay, that means that the domain is going to be every real number, but you can see the range, okay, that vertex is still the turning point of the parabola. So the largest y coordinate that I see is 4, and then my y coordinates just fall downwards forever. So that's my range. So that means that if I want to pick an x value to substitute in, I can sure pick any real number, but if I want to pick a y coordinate to substitute in, it has to lie between -infinity and 4. So if at this point something goes wrong for you, it's possible you've substituted in a value outside of the range of the function. So here we may as well pick y to be 0 because we can. Doing so, we'll get x minus 8 all squared is equal to -2 times 0 minus 4. If we solve here, we end up with x being 8 plus or minus 2√2. And so that gives us a point when y equals 0, x is either just shy of 11, and we also get another point for free on the other side of the axis of symmetry. There. So we can now sketch in our accurate parabola. As so. Now notice in these last two examples where our vertex isn't at the origin, I've not been memorizing the formulas for where the focus is and the directrix. I've just placed the vertex where I know it is and then used distances, used that p-value to map out where the focus should be, where the directrix should be, and if I open left, right, up or down. Okay, so in practice, you don't always need to remember those formulas. You need to be able to work with them behind the scenes. Let's look at these last three problems together a little bit quick fire. So, graph x squared equals 4y. The fact that the x term has the square means we have a vertical parabola. The fact that p is positive, okay, we'll calculate exactly what it is in a second, but p is positive, so that means we open upwards. Our vertex is at the origin, 0, 0. We can read that off from the equation. What's p? Well, comparing, we know 4p is always that coefficient, in this case 4, so that means that p will be 1. So I have a parabola that's opening upwards, so that means my focus will be 1 unit above the vertex. My directrix will be 1 unit below the vertex, and the axis of symmetry will skewer through the vertex and the focus at x equals 0. So let's record this information. We know the focus is at 0, 1. The directrix is at y equals -1, and our axis of symmetry is at x equals 0. Let's now take another point on the parabola. So this is where I can be a bit clever with my x choice. Okay, if we take x to be 2, well then I get 2 squared equals 4y. The 2 squared gives me the 4 to cancel with the 4 on the other side, so I get y equals 1. So that means I have a point at 2, 1, and the axis of symmetry gives me a point for free at -2, 1. I can now draw my nice opening upwards parabola. Next, let's look. We want to graph the parabola whose focus is -5, 0. So that's 1, 2, 3, 4, 5. That's our focus, and the directrix is at x equals 5. So 1, 2, 3, 4, 5. Our directrix is there. So a couple of things we can immediately note down. The vertex is always halfway between the focus and the directrix. So on that line segment joining the focus with the directrix, the vertex is halfway between. So the vertex is going to be the origin. I can read off what P is, right? At least in absolute value. Absolute value is supposed to be the distance from the vertex to the directrix, or the vertex to the focus. In this example, that distance is 5. Notice though, we're going to have a horizontal parabola opening to the left. We always wrap around the focus. So the fact that we're opening to the left means that P is going to be negative. So P must be -5. I can now substitute into our equation, right? For a horizontal parabola, this is the equation that we use. It's the y term that gets squared. We just figured out that P was -5, so we get y squared equals -20x. Let's get another point on the graph to play with. Is there a clever choice that I can make? Well, I know to solve for x, I'm going to have to divide by -20. So if I take y to be, say, 10, that division will be really nice. Okay, so at the left-hand side, 10 squared is 100. So when I divide, I'll get x equals -5. So the point for free that I get is at -5, 10, which is somewhere off our graph paper up there. What about my axis of symmetry? Well, I know the axis of symmetry is at y equals 0. So I get another point for free, x equals -5, -10, down there somewhere. So when I complete the parabola, this is what we get. Finally, okay, it wouldn't be a conic sections example problem section if we didn't have to complete the square at least once. That's the strategy here. So we have our y terms, we're going to complete the square. Because it's a parabola problem, there is no square attached to the x, so we actually only have to complete the square once. When I do that, I'm going to say y squared plus 2y. Need to add something to make that a perfect square. What am I going to add? Well, I'll add 1. I then need to be sure that I subtract 1, of course. I can now factor this as y plus 1 all squared is equal to, now the left-hand side is going to be -12x plus 24. But that's not quite standard form yet. I need to pull out a common factor of -12 to make sure that I just see an x by itself with a coefficient of 1 inside the bracket. Then I'll subtract that 2 to make the algebra work out. So now we have our equation in standard form. Let's graph it. So I know my vertex has x coordinate 2 and y coordinate -1. So we'll have 2, -1 as our vertex. Here, that's our vertex. What else do we have? Well, I know because the square is attached to the y bracket that our parabola will be horizontal. Looking in standard form, we can see that P is negative, so the parabola will open to the left. I can now even solve for P. For P is going to be that coefficient of -12, so P is -3. So to open towards the left, that means my focus will be to the left of the vertex. So my focus is 3 units to the left of the vertex. My directrix will be 3 units to the right. My axis of symmetry will skewer through the vertex and the focus. So axis of symmetry at y equals -1. Now all we need is an additional point on the parabola. What will we pick? Well, I'll leave it as an exercise for you that if you pick y equals -7, you can solve and get that x is -1. So I get a point on my graph at x equals -1, y equals -1, 2, 3, 4, 5, 6, 7, and another point for free on the other side of the axis of symmetry here. And now I'm able to draw a beautiful parabola passing through those points and the vertex. Pew. One very last point to discuss about parabolas is their lattice rectum. So that is the line segment that is parallel to the directrix that passes through the focus. So it's trying to do the best of both worlds. It wants to pass through the focus but be parallel to the directrix. This line segment will always have length 4p, at least when we take the absolute value of p. So that's just one more way in which p is controlling the shape of our parabola. This can also help us look for nice test points if we're interested in finding the shape of our parabola. We can include the lattice rectum rather than picking a random test point. That will tell us how wide or narrow to make our parabola. Of course, if p is too large, 4p is going to be even larger, so maybe it will be off our graph paper, but it doesn't hurt to go looking for it.